I'm Xian Kim from Ewha Women's University. Today, I'm here to present a paper, A Robust Counting Sketch for Data Plane Intrusion Detection. The contents of my presentation are as follows. Network traffic measurement is an important task for intrusion detection, and analyzing per-flow statistics is considered essential. Per-flow measurement is sometimes performed using a gateway approach such as NFV for scalability, but its operational cost is high. Recently, in-network computing approach using programmable switches has emerged. Modern programmable switches meet the expectations of internet service providers due to the high-speed packet processing capacities, high flexibility by customizing functions in the data plane, and low cost compared to legacy switches. Because of these advantages, hardware-based and sampling-based and sketch-based approaches have been presented for in-network per-flow measurement. Hardware-based approach uses TCAM, thus it is fast, but it has a scalability issue due to the scarcity of TCAM. Sampling-based approach could be a viable option, but it has a low measurement accuracy. Because of these trade-offs, sketch-based approach became a promising scheme with lightweight computational overhead and low memory usage. Sketch is a compact data structure that counts a large amount of data. Sketch have been widely used because of its high accuracy and feasibility in resource-limited switches environments. Examples of such sketches include count-min sketch, elastic sketch, and FCM sketch. The figure below shows the example of count-min sketch. Count-min sketch is a data structure that with a total of D layers consisting of W counter arrays. When an item comes in, D hash functions are used to locate the item at different counters in each layer. During the encoding, the counter value in each layer is increased by 1, and the minimum value among them becomes a decoding value. To effectively use sketch in network traffic measurement, a skewed data structure has been introduced to accommodate Zipfian distribution of traffic. Elastic sketch and FCM sketch are examples of using the skewed data structure. These methods give smaller counters to a mouse flow filter and larger counters to the elephant flow filter. These are aimed at multi-stage filtering, where multiple sketches are cascaded sequentially to filter flows by size. For case of elastic sketch, it first uses TCAM to filter elephant flows, and then stored kick.mouse flows in the count-min sketch. FCM sketch has a data structure that reduces its counter size as the depth of the tree increases. It encodes flows from the lowest layer and cascades to the next layer only when the counter is saturated. Intuitively, these methods can work well on a particular flow size distribution. But these approaches cannot be a viable option due to the characteristics of the traffic. The flow size distribution, FSD, of a traffic is unpredictable and varies by manufacturers. The figure on the left side shows the similarity between real-world datasets and self-generated skewed datasets using KS tests. In the figure, the numbers of the name of the dataset indicate the different flow definitions. As can be seen, the different type of datasets results in different skewness, and it also varies depending on the flow definition. The figure on the right side shows the change of FSD in the same data stream over time. As a result, even if the sketch reflects the Zipfian distribution, it is difficult to measure traffic with a sketch that is tailored to one particular distribution. Therefore, it is a challenge to create a robust sketch that adapts to various traffic patterns. There is a simple solution to overcome the challenge: the reconfiguration of the data structure with proper parameters. To perform the task online, dynamic schemes that change structures during the encoding have been studied. But this cannot be implemented in the programmable switch, and it also inevitably adds overheads to the packet processing pipeline. In the case of reconfiguring sketch offline, changing the data structure requires recompile and reload. This results in a high delay, which can be several seconds. so it is not easy to change the data structure of a sketch on the fly without such downsides. Therefore, designing a sketch that adapts to various FSD without reconfiguring the data plane is another challenge. To overcome the challenges, we designed Countless, a robust and accurate sketch to embrace various FSD. Countless works well under both attack and benign traffic without dynamic adjustment of data structure. We introduced a new flexible encoding method called minimum update, which achieves high accuracy by using memory effectively. We provide theoretical proof of the error bound, and evaluations on security application verified its robustness. And Countless is implemented on the Tofino programmable switch, showing feasibility of in-network flow measurement. Countless has a multi-layer data structure, with a total of D layers. The highest layer consists of 32-bit counters, and it halves the counter size going down to the lowest layer. By introducing the factor R, a lower layer array possesses R times more counters than its upper layer. With this structure, the hash collision probability of lower layer decreases. Using the pyramid-shaped data structure, conservative update algorithm is considered optimal in Countless. The figure below shows the encoding process Countless with conservative update. When a packet comes in, it first finds a global minimum value by checking counters across all layers. After that, it only updates the minimal counter value to avoid unnecessarily adding nodes to the sketch. While achieving high accuracy with conservative update, it cannot be implemented on the data plane of the switch, since double access to the same region is not allowed. To deal with the issue, we introduced a novel encoding method called minimum update, which is an approximate version of a conservative update. Unlike conservative update, minimum update strategy updates counting sequentially following the lowest to highest order. During the process, it calculates and stores the temporal minimum value. In each layer, update happens only when the value is smaller than the current minimum value. The left figure shows how the minimum update works effectively. As you can see, it updates its counter sequentially from layer 1 to layer 3, and during the encoding, it skips layer 2 since its value is larger than the current minimum value. This example shows the noise reduction effect of our update strategy. The figure on the right side shows a worst-case update where the global minimum value exists in the highest layer, causing undesired updates through all layers. But taking advantage of the pyramid-shaped data structure, the lower layer is likely to have a global minimum value, so such case probability is small. Countless and FCM have the same data structure, but there is a big difference in their encoding methods. FCM counts a flow on a single layer and cascading it to the next layer when counter overflows. But Countless encodes flows across all layers regardless of their size, so flows of various sizes can be decoded using all layers even when some of the counters are saturated. The figure below shows the example of two schemes where some counters overflowed. Because of the saturation of layer 2, the decoding value of FCM becomes much larger than its actual value. Unlike FCM sketch, Countless shows that the flow can be decoded sufficiently in layer 3. Maximizing counter uses across all layers leads to a reduction of hash collision rate, thus Countless become more accurate in various flow traffic patterns. Because of this different encoding strategy, Countless and FCM show different bitwise counter usage. Using a data set with 99% of mouse flows, Countless used all three layers, maximizing its counter usage. On the other hand, FCM mostly uses layer 1 counters since it strictly partitions the layers based on the flow size. To analyze schemes in detail, the matrix called flow survival rate was introduced. Flow survival rate is defined as the fraction of flows that are below a certain relative error after decoding. In the figure, the higher survival rate indicates less estimation error, and layer number means where the flow is decoded. Comparing three schemes, Elastic Sketch shows better accuracy than others for mouse flows, since it uses most of the memory as an 8-bit counting sketch for a mouse filter. Other than that, Countless outperforms other schemes and show that flows can be decoded in all layers regardless of the flow size. To evaluate robustness of three schemes, we created artificial network traces by varying the zip skewness. The smaller skewness means more elephant flows in the network trace. Elastic Sketch has better accuracy with elephant heavy trace since it uses TCAM-based elephant filter. Other than that, Countless provides better accuracy than others under various skewness. With these results, Countless shows its ability to embrace dynamic traffic changes. We also conducted experiments for various security applications. We used 3 real-world data sets that have different flow size distributions. Countless verifies its robustness, providing stable, more accurate, or similar estimation results comparing 4 schemes with single parameter setting. We analyzed the data plane overheads of 3 schemes using programmable Tofino switch. Because of its simplicity, count means resource uses is the lowest compared to other schemes. Other than use stages in the data plane, the resource consumption of Countless is lower than FCM Sketch. And regardless of more used stages, the total latency of Countless is only 57% of FCM Sketch. Flow size distribution changes by many factors, such as the type of the dataset, definition of a flow, and even over time, thus unpredictable. Therefore, we designed Countless, a robust and accurate sketch that adapts to various traffic patterns using a novel update algorithm called minimum update. Countless is implemented in the Tofino programmable switch, showing low latency and high throughput. In addition, the various evaluations using self-generated datasets and real-world datasets verified high accuracy and robustness of Countless.